Hello everyone. In today's video, we will be continuing from where we left off in the previous one. Now, near the end of that video, I had said that we will be making the physics of the simulations much more realistic by adding bounces. So that's what we will be doing in this video. If you have not watched the previous one, please go ahead and watch it to get a better context of the physics and the code involved. You can find the link in the description down below. So here is the agenda for this video. First, we will be making some animations for the ball going up and down, something like this. And then we will be writing some code for the ball to bounce the moment it hits the ground. Of course, there will be animation, something like this. Finally, we will be making the physics more realistic by making the ball lose energy every time it hits the ground. And of course, we will be making some informative animations like this. So I have added some timestamps and chapters across this video here. And if you want to skip ahead to some particular section, then you please go ahead. And yes, I am using my bottle as a mic stand here. Alright, let's start coding. Alright, so we are back with our friendly neighborhood 1D equations of motion here, and for this code today we will be using these 4 packages mainly. So I have already introduced you to NumPy and PyPlot in a previous video. For this code, the additional 2 packages that we will be using is GridSpec, which is used for placing plots in a particular position in the figure, which you will get to know later in the video, and the func animation for creating our animations. I've also defined 2 variables here. The g is the acceleration due to gravity for Earth, and the value is 9.81 meter per second square. And a is the acceleration experienced by the ball throughout its motion, so which will just be the negative of g. I've also defined these 2 functions here, which we will be using throughout our code for getting the velocity and getting the height. The velocity takes in the initial velocity and a time parameter and uses the equation of motion to return a new velocity value. Similarly, height takes in the initial height, initial velocity, initial time, and returns the calculated height value through the equation. And I have just used these 2 lines to create a folder named animations where we will be storing our animations. It's just helpful in more organization. Okay, so for the animation part, I have also defined one function here which we'll be using for making our simple animations. Let's see how it works. So firstly, we are creating a figure and an axis object separately. So in the previous video where we had used plt.plot, the figure and axis are implicitly defined. But here I want these 2 objects explicitly in my control, which is why I am defining figure and ax as separate objects here. Then I am defining the x limit of the axis. So what is the range the x-axis will span? And similarly, what's the range the y-axis will span? And then I am giving a name to the y-axis here. And then I'm setting the x-sticks to be nothing. I don't want any markings on the x-axis. You will see later on why I did that. And then I'm setting the grid to be true, so I want grids in the plot. Then how do I animate the motion? I'm basically first defining an empty ball here, or it's simply a point, but I'm just naming it ball, and which is blue in color, and O is just the marker style. Then we're calling the func animation, which we had imported here, and passing the figure object that we had defined here, the update function. Now this function takes in the frame value, and then we'll set the new data according to that frame value. So we will be setting the new coordinates of the ball with each frame, and then we'll just be returning that ball again. The rest of the parameters that the func animation requires is frames, which is just the array of frames that we want to use for our animation. And then the interval, which is basically after how long will the next frame be called. And lit is just for smoothing, which we don't need now. And I'm saving the animations in the animation folder. So let's just run this now. Now since we need the height values for the animation, let's just bring back our code that we had written in the previous video and run it again. Now as I had explained that I'm setting the limits of the y-axis manually, I would like the maximum height to be a parameter for the y-limits. So I'm basically defining the maximum height that will be attained by the ball. And this you can derive from the third equation of motion by setting the final velocity to be 0. And then I'm calling the function that I had defined for animation by passing the height values, the time values as the frame array, and then the x-axis limits, and the y-axis limits from 0 to height plus 1. That plus 1 is just for some space. And height will be the label that will be printed on the y-axis. And 50 is the interval, 50 milliseconds is the interval between each frame, and freely falling body here is just a file name for the animation. So running this will take some time, and let's just skip ahead. Okay, now the code is run, and we can see we got a very static image. So to view the animation, we can just open the GI file here, and you can see that we have created a nice animation for the ball going up and down. So since we have not added any bounce yet, the ball just stays on the ground for a few seconds. and it's repeating because it's a GIF image, by the way, it's not bouncing again. And we can also observe that the velocity of the ball decreases as it reaches its maximum height as predicted by the physics equations. Alright, now let's add bouncing. For now, the challenge is more of a coding one than a physics one. So we will talk about the physics when we are adding the condition of losing energy each time the ball bounces. For now, let's just focus on the coding part. So how do we make the ball bounce? Firstly, we are defining some initial parameters of the initial velocity, which is 10 meter per second, initial height, which is 0 meter, and then we are defining the time values arrays. So it starts from 0 to 10 seconds with a difference of 0.01 seconds between each time value. And then I'm defining the height and velocity arrays, which is empty for now. Then I'm setting a counter, which is a time counter. I'll explain why. Let's understand the logic of making the ball bounce. Now there might be some other ways of making the ball bounce as well, but this is the best one I could come up with on my own. So here we have the time values array, which starts from 0 seconds and ends at 10 seconds, and the difference between each time value is 0.01 seconds. Now let's divide this entire array into blocks, and the length of each block is the time taken for the ball to go up and come back down. That is called the time of flight of the ball. So basically, in this block the ball would go up and come back down within this time period, and then it will repeat the same for each block here. Now earlier when I was simulating and animating the motion of the ball, I had let the time variable in the for loop access each and every single time values in the array. Problem with that is that the equation of motion don't care about the bouncing. So for this case, if we let the time value keep on increasing and increasing, the ball would just continue descending and it would not really simulate the bouncing. Now since the time value is the actual controlling factor of the motion here, what we can do is the moment it touches the ball, we'll just reset the time value counter and then restart the motion again, but at a different position now. So after the ball reaches the ground here, the time value will again set to 0 and then restart its motion here, but it will be shifted. So that will give the simulation of bouncing. Okay, so we are back with the code now. What we will do is we'll set a counter variable for a time value and we'll just initialize it as 0. Since we want to know when it bounces, we are also using a bounce counter here. And then I am going through the parent time values array here, which we had defined here. Now this underscore here means that there is no representation for the counter variable that will go through the time arrays. Since we don't need one, we are explicitly using one here. First we will get the value of the height here, and then we'll check whether this height value is lesser than the initial height. If it is, then we will just set it to the initial height here and we'll increase the bounce counter here. And then we will reset the time factor. So the next time the for loop runs, this will start with t equal to 0 and then it will again give me the initial values of the height. So if this is true, then these values will be modified here, and then again we'll calculate the velocity and just will append these values to the list here. And then after this, all this process is done, we'll just increment the time counter by the dt, which is 0.01 second. And again the for loop will repeat and we'll check if it's lesser than the initial height or not. Now since I had talking about time of flight, let's also include that factor here. Now to get the time of flight, we basically have to use the first equation of motion and set v equals to 0. The maximum height, the velocity will be 0, and we get the time taken to go up there. Now since this motion is symmetric because there is no other force acting on the ball throughout this motion, we can say that the ball will take the same amount of time to reach the ground, which is why we can just multiply by 2 and get the total time of flight. So the equation becomes t equals to minus 2 v naught by a, and that's what I have defined here, minus 2 times v naught by a. And now let's plot the time values against the height values to see whether it's bouncing or not. And we can see that it's giving us a nice bounce curve here. The ball starts rising and reaches a maximum height of almost 5 meters and then comes back down, and this is where the resetting of the time counter is happening. The moment the height value is lesser than the initial height, the time counter is getting reset. So the next time the height value is calculated, we are again restarting the entire motion here. And this is how we can simulate the bounce motion of the ball. And we can see that total time of flight is 2.04 seconds, which means that the ball takes almost 2 seconds to reach the ground here, and we can see that that is true because the ball reaches the ground almost 2 seconds here. Remember, the x-axis is time axis. And then we can similarly plot the time values versus the velocity values, and we can see that the initial velocity starts from 10 meters per second, goes to minus 10, and again starts with 10. That's because I had reset the time counter to 0, and so again the calculations restart and we get this periodic motion here. So let's animate this, and again we are defining the maximum height that the ball will reach for the y-axis limits, and running this, it takes a while. Now while the code runs, why don't you like the video if you found it informative till now, and subscribe to the channel. So the code is run and we again get the static image here, and if we want to view the animation, we can just go here. And this is our animation of a bouncing ball. The ball goes up, slows down till the maximum height and comes back down. Note that the velocity increases and then now it bounces, since the height value would be lesser than 0 there and the entire animation is reset there. And again it goes back up and comes back down. Now notice that the maximum height reached is the same for every bounce, which is not realistic, and that is what we will simulate now. Now I think everyone can agree with the fact that the simulation we just made for the bouncing ball is not realistic, because the ball is reaching the maximum height again and again. Now what happens when a ball touches the ground after it comes back down? It loses its energy in the form of heat, sound and other rotational kinetic energies. And so the next time the ball goes up, it should not reach the maximum height. All of the loss of energy can be characterized by one single number, which is called the coefficient of restitution and denoted by E here, and the formula is this one here. So Vf and Vi are the velocities of the ball after and before the collision, whereas Uf and Ui are the velocities of the surface that is colliding with the ball. Now if the surface is rigid like the ground we have, then this values would be 0. So we would get just minus Vf by minus Vi. Now the range of the E value is from 0 to 1, where 0 means that there is no bounce and there is a total loss of energy, whereas 1 means it's perfectly bouncy and the ball will reach the maximum height again. And so basically the previous animation that we had made, we were simulating for E equals 1. Now for our scenario, when the ball is going up and down with no rotation, the E value can be related to the other values in this fashion here. Now energy loss, the impact, can be characterized by E since through this equation here. So essentially we have 1 minus E squared times 100. Let's analyze the decrease in velocity after each bounce at a closer detail. So here the superscript 0 denotes the initial velocity of the ball after each bounce for each iteration, whereas the subscript number denotes the bounce that the ball is approaching. So V01 is the initial velocity of the ball that is approaching the first bounce. So that would be the initial velocity of the entire motion itself. Now V02 would be the initial velocity of the ball that is approaching the second bounce, that is after the first bounce, and that is simply the initial velocity decreased by a factor of E. Similarly, V03 would be V02 times E, and since V02 is already V01 times E, so we can get V01 times E squared. And if we generalize this trend, so we can get this equation for the initial velocity of the ball that is approaching the nth bounce, and that is given by the initial velocity of the entire motion itself multiplied by e power n minus 1, where n is the nth bounce. We can get similar expressions for the maximum height reach in the nth bounce and the time of flight for the nth bounce. Please note that the factor of 2 here is because h is directly proportional to square of e. Now since this is a geometric progression, we can get the total amount of time taken by the ball for n bounces to be from this formula here. Alright, let's code this now. Almost everything is the same. We are defining the initial parameters v1 and h1, and then we are again defining the parent time values array. The only difference now is that we are including the factor of e here. So for this example, I am just assuming the e to be 0.7, which means the velocity of the ball after the bounce would be 70% of the previous velocity. So 30% is lost in other forms of energies. And we are also including this Vn. So we are again calculating the height values here, and we are checking whether this is lesser than the initial height value. If it is, then we are resetting the height value here, and then we are incrementing the value of the bounce. Now this time we are recalculating the initial velocity value by multiplying the initial velocity of the entire motion by e to the power of bounce minus 1, which is just n minus 1, and then resetting the time value again. And we just redo the entire calculation and repeat the for the entire motion. So let's plot this motion. And this is the plot of the ball bouncing. Please note that the maximum height decreases after each bounce here, and also the time of flight of each iteration decreases. So that means that this is not a periodic motion anymore, because the energy is lost after each bounce, so the time taken for the ball to be in the air also decreases, and eventually it just goes down. Similarly, we can plot the velocity values as well, and we can see a similar decrease in the velocity value to almost 0 here. Let's again make another animation for this bouncing ball using the same function that I had defined earlier. So the code is run and we get a static image as always. So let's just view the animation. And this is the animation of the ball which will experience energy loss after each bounce. The ball comes back down and now it bounces, and notice the maximum height that it will reach, which is much lesser than what it had previously reached. And again the maximum height will decrease, and it just keeps on decreasing and decreasing. Now let's look at how the energy values change throughout the motion. So here I'm defining the mass of the ball to be 1 kg, and I'm again defining the same energy values that I had defined in the previous video as well. So the potential values is here, the kinetic energy and the total energy here. Now I'm using grid spec to divide the entire figure into two halves here, where I have defined one row and two columns. So here's the plan. On the left side, I will have the ball motion going up and down, and on the right side, we will check how the kinetic energy changes. So it would be better to just show the animation than explain this entire code here, because this is just plotting. Alright, the animation is done, and again we get the static image. So let's just view the animation. And here we have the animation that we just made now. So as the ball goes up, the potential energy increases and then decreases. And note how the entire energy is decreasing with each bounce. The total energy stays constant throughout the motion and then decreases when the ball bounces. So the energy lost after each bounce is almost 51%, because remember in the equation we had 1 minus e squared, and for this example I had used e equal to 0.7. So that gives me almost 0.51, and multiplied by 100% will give me 51%. So this is a very informative plot about how the values of the energies change for the ball as it goes up, down and bounces back with energy loss. Alright, I hope you enjoyed the video and learned something new. Like the video and share it if you did, and please subscribe to the channel. You can check out the code in the GitHub repository, whose link is down in the description box below. In the next video, we will take one step further in with the realism and simulate the ball falling through a viscous fluid and reaching terminal velocity. So if you want to check it out, go ahead and subscribe to the channel. Thank you, stay curious.